Thank you. Welcome back. So this afternoon we continue with the theme of eminent speakers, two of whom are presenters on the Sky at Night. So to make up for the fact that I overran in my lecture, I'm not going to go on for too long in these introductions. But I'm here today to firstly introduce Chris North to you. Now, Chris studied at Cambridge and Oxford and then topped the triumvirate by becoming a presenter on the Sky at Night. He's working now as a postdoc at Cardiff University, where he works on the Herschel Infrared Space Observatory. He's also published his first book, and that was with Patrick Moore, and it was called The Sky at Night Questions. Was it Questions and Answers from Across the Universe?
Yeah, I think so.
It was answers to questions from across the universe, thereby completely trumping me because the book that I wrote was called The Big Questions, and I never promised to answer any of them on the cover. Chris will do a much better job than that. Ladies and gentlemen, Chris North.
Thanks, Stuart. Is the mic on? Can everyone hear me? Yeah. Excellent. So, thanks for the great introduction. I'm going to talk today about the Herschel Space Observatory, which is a European Space Agency observatory launched in 2009. We have a heavy involvement with it, not only in the UK, but also specifically in Cardiff, where the lead scientist, the principal investigator of one of the instruments on board is based. Which is why I'm based in Cardiff. As I say, the UK has strong involvement, and it's been doing some great stuff. Launched a few years ago, discovering all sorts of things about star and planet formation and galaxy evolution, which I'll try and run through. But I'll start off with a little bit of history. So, the top image of these three is an image from 1785, taken by a chap whose name is somewhat familiar to me, a chap called William Herschel. His name will crop up a couple of times in this talk. He was trying to make a map of the galaxy, so he was very rigorous in his observations and trying to pinpoint the positions to all the stars and where they were and their distances from Earth. Now, they didn't have a hugely accurate way of doing this, which is why the picture at the top looks like, I think it looks like a space amoeba, but it looks like a general blob. I think the sun is meant to be in the centre, where there's that tight cluster of stars. And it's got a few things right, such as over on the right here, there's gaps in the galaxy. We now know those to be dust layers, where in fact there are stars there, they're just hidden by clouds of dust. So he's got the general structure of the galaxy being a disc-shaped thing, a flattish object. But it's a long way from what we now understand the map of the galaxy to be. So that was 1785. Come on to about 100 years later, to 1887, and one of the first astronomical photographs of something called the Great Andromeda Nebula. So this is taken by a chap called Isaac Roberts, who I think was a Welshman. So that's what we now call the Andromeda Galaxy, and we now know it to be something that's an object that's outside our own galaxy. But in fact, it may surprise people to learn, it's been less than 100 years since we had confirmation there were galaxies outside our own. So a chap who's shown in the bottom right there, who's probably a bit small to be able to see, is a chap called Edwin Hubble, who also has a space telescope named after him. And Edwin Hubble in the 1920s proved that the Andromeda Galaxy was much further away than any of the stars in our own galaxy, and that was in the 1920s. So it's less than 100 years, less than a century since we proved there were galaxies beyond our own. And since then, our understanding of the universe has expanded enormously. So, the image on the right is something called the Hubble Ultra Deep Field. You've probably seen this image or images like it before, where every galaxy is every dot in there is a galaxy. And they did that by staring at a patch of space to see what they could see. And now a lot of astronomy is done by doing just that, by staring at a tiny patch of sky that is otherwise unremarkable and seeing what's there, and staring at hundreds or thousands of galaxies at distances of millions and billions, in fact, of light years. And then on the left, we've got a map of the large-scale structure of our universe. So the Sun, the Earth, and our galaxy are the centre of this image. And you can see two fans spanning outwards. This is a survey from the Sloan Digital Sky Survey, and that is showing every dot in that image, and there's about 500,000 galaxies there. Every dot in that image is a galaxy. There's about 500,000 galaxies there, and it's showing the galaxies are clustered into walls and with voids between them and so on. Now these are taken at optical wavelengths with visible light, and have told us an awful lot about the structure of the universe. But we have a vague idea of how the universe has evolved over time. So here's the big picture of how the universe has changed. So on the left, at the start of time, you have the Big Bang. The Big Bang caused the universe to expand very, very, very rapidly in a period called inflation, and then it was opaque for a few 100,000 years, and we got something called the cosmic microwave background radiation release. That's something that I don't have time to talk about today. After that, we have something called the Dark Ages. The Dark Ages is where Isaac Newton was doing his work. We had a universe that was full of neutral hydrogen and helium gas, just slowly collapsing under gravity. And eventually, it got dense enough and pushing hot enough in the centre of one of these clumps of matter for nuclear fusion to start, and that's what started the first stars. And a few 100 million years after the Big Bang, maybe a bit less, maybe a bit more, we had the first stars. Those stars moved into galaxies. The galaxies have changed and evolved over time, and eventually you get planets and moons and comets and spacecraft looking back. And in fact, Herschel is looking back at a lot of that history of the universe, of how galaxies have formed and changed, and how stars have formed throughout the history of the universe. So why is it called William Herschel? Well, why is it called the Herschel Space Observatory? It's because of this chap William Herschel. So here's a picture of him in his laboratory in about the year 1800, so just over 2 centuries ago. And he's doing an experiment to look at essentially the heat carried by light. So he's taking sunlight through a prism and expanding it into his rainbow, and he's shining that rainbow onto some thermometers. And he's saying, well, which wavelength, which colour gives more heat? And he correctly deduced that blue light gave more heat than red light. Blue light carries more energy, and you can tend to be hotter than red light in some respects. What he then did is he had a thermometer as a control, set a wavelength spectrum over to one side, and beyond the red. And he discovered that was still getting heated up. There was light that was coming through the prism, not being part of the rainbow you could see with his eyes, but there was still some energy from the sun was heating up this thermometer. Something that was invisible light that he couldn't see, that was nevertheless impacting the thermometer. We now know that to be called infrared radiation. It's longer wavelength light than the light we see with our eyes. And because of his discovery of this light, that's why the Herschel Space Observatory is named after him. The infrared light is one of many regimes of the full spectrum of light, something called the electromagnetic spectrum, that is now known to exist all the way from radio waves, through microwaves, infrared light, visible light, ultraviolet, X-ray and gamma rays, a full regime, and we actually use that full range in astronomy. Where Herschel falls in is, if you can see the blue bar at the top, Herschel falls in here somewhere. It's what we call far infrared light, so that's long wavelength infrared light, and into something called the submillimeter, so the way that the light is a reasonable fraction of a millimeter in size. We can also attribute temperature to these different wavelengths. So you can say what temperature is an object that is emitting that wavelength of light. So for example, visible light is typically emitted by objects that are very hot. So objects like the sun. So the surface of the sun is about 6,000 degrees or thereabouts. And that emits primarily visible light, most in the green spectrum, a little bit in the red and the blue, and then a little bit side to side of that and so on. But primarily in the visible light. If you go to long wavelengths, you're generally seeing stuff that's emitted by colder objects. So the light that Herschel looks at is the wavelength of the light is 100 to 1,000 times longer than the visible light that we see with our eyes. And that means we're looking at stuff that's 100 to 1,000 times cooler. So instead of looking at things that are thousands of degrees, we're looking at things that are tens or hundreds of degrees above absolute zero. Bear in mind that absolute zero is minus 270 degrees C. We're looking at things that are minus 200 and something degrees C in temperature. Very, very cold indeed. And that stuff does exist out in space. In fact, we can see this from a chart of how bright the sky is at different wavelengths. So there's not many graphs in this, but here's one. So up the left axis, the vertical axis, we've got the brightness of the sky, and average of the sky, how bright is it? And on the horizontal axis, we've got the wavelength of the light we're looking at. So on the left, we've got visible and optical and a little bit of a near red light. And you can see that yellow line is showing that's the light, that's how bright the sky is at those wavelengths. That's the light the stars are emitting. So stars primarily emit at wavelengths of about 1 light, for example, or a bit shorter. And that's how bright the sky is. Well, what happens if you go to very long wavelengths? Ooh. My animation is broken. I can't show you what happens at very long wavelengths, but I can draw it for you. There's another peak here, which is a peak by this longer wavelength light, which is emitted by dust and gas between the stars. And that peak is at the same temperature. The sky is just as bright at those wavelengths as it is in visible light. And so if we ignore the light that's emitted at longer wavelengths, we're ignoring half the stuff in the universe, which can't be good for getting a better understanding of it. So we want to look at long wavelength stuff. Why isn't the Herschel Space Observatory? Why not build it on the ground? Well, here's a plot of how opaque the atmosphere is at different wavelengths. So again, we've got radio waves way on the left, and we've got gamma rays way on the right, and everything in between. So visible light is somewhere here. The darkness of this graph, and the height of the line, tells how opaque the sky is. So radio wave is transparent, it's fine. Visible light, it's pretty transparent. So that's why we have telescopes on the ground, albeit up high up on the mountains traditionally to do the best work. But if you go to the wavelengths that Herschel is looking at, you can see that this graph is pretty black, it's very opaque. The sky is essentially opaque at these 5 red sub-nanometer wavelengths. So you have to get above the sky, essentially. Now you can do that by going on a very, very high altitude balloon. You can only do that for a few days or a couple of weeks at a time. The best way of really doing it is to go into space. And so that's why Herschel's launched. It doesn't just go into Earth orbit, it's gone much, much further than Earth orbit. It's gone to a point called the L2 point. It's 1 million miles away from Earth in the opposite direction of the Sun. So it's 1.5 million kilometres. It's a special point in space. So traditionally, if you went further out from the Sun, you'd be orbiting the Sun slightly more slowly. So instead of orbiting the Sun once a year, as the Earth does, you'd orbit the Sun in 1 year and a bit. From the point of view of the Earth, it gradually drift away. The L2 point is special because as well as that gravitational pull of the Sun making you orbit, you've got a little bit of tug from the Earth itself as well, which is only 1 million miles away from there, and that increases your speed just enough to mean you orbit in exactly 1 year. So you stay in sync with the Earth. It's a very useful point, and it's the local holiday destination for many of the upcoming space observatories that are going to be launched by ESA and by NASA. So Herschel's gone to this point 1 million miles away. What does it look like? That's a picture of Herschel. Its main mirror, which is this dish here, is 3.5 meters across. So it makes it the single largest, or the largest solid mirror ever launched into space. I can't say it's the largest mirror launched into space because there are radio telescopes up there with larger mirrors. They unfurl those when they're orbit, which I call cheating. But this is the largest solid one ever launched. So 3.5 meters across, the whole thing weighed 4 tons on launch. And below that main mirror, there's a black can, and that contains the scientific instruments. And the scientific instruments are cooled down to very, very low temperatures. They're cooled down to temperatures of 1/3 of a degree above absolute zero. That makes them the coldest place in space, that we know of, which is quite cool when we get fun. So there's 3 instruments, 3 cameras there, looking at a very wide range of wavelengths between them. Obviously, this wasn't just built by a few people. There's a group of people in 2010 at the first science meeting about the results from Herschel. There's a few hundred people there, and that doesn't include many of the technicians and engineers working on the satellite itself and keeping it in orbit. I am there, taking up about 6 pixels, I think, in that image on that screen. But that was a great meeting to go to a year after launch. This is what the satellite looked like if you took off the main mirror and so on and lifted all that up. So this is when we were still in the lab. The three instruments are there labelled. They've got acronyms as names. So the one I work on is SPIRE. It's a Spectrum and Photometric Imaging Receiver. And the others have long names as well. But each one is about the size of a tabletop, I guess, if you were sent to scale. And they stare up at the secondary mirror, which is reflecting the light from the primary mirror. Now, how do you get a satellite this big into orbit? Well, the first thing you do is you stick it on a plane. You stick it on a plane and send it to French Guiana. So Indiana Jones style, there we go. You're down in French Guiana. Incidentally, it's one of the only planes I've seen with a nose cone lifts up. I guess you get some mail freight in the US or like that. And this big canister that's being hauled in, it's got Herschel inside it. You fly to French Guiana because that's Europe's spaceport in Kourou, European Space Agency spaceport, and you stick it in the top of an Ariane 5 rocket, so Europe's largest rocket. Herschel is currently on top here, with the top of the rocket being lowered down, and in this black can is its sister mission, if you like, launched at the same time, called Planck, another satellite, which I don't have time to talk about today. And they're sitting in the very top of this rocket, and of course the important thing to remember about rockets is they're mainly fuel. So once you've got them in the rocket, obviously you want to launch it. So here's a not great quality video. I don't know whether that's... I can even come out into the speaker. There's only a rocket noise. So the launch, I was lucky enough to be there. It was absolutely amazing to see. If you get the chance to go and see a rocket launch, I truly recommend it. So launching off the first one, it's solid rocket boosters, and the important thing to remember about solid rocket boosters is that they're essentially controlled bombs. They have a bit of solid fuel in there, and you light the solid rocket fuel, and you cannot stop it once you hit it. And you hope everything comes out back on the bottom. And if it doesn't, then you have severe problems. Luckily, that very, very rarely happens. There are problems, and everything went very smoothly, and the launch went very, very well indeed. And Herschel and Planck were put on an excellent orbit to send them out a million miles away. It took them about 6 weeks to get there, whereupon they started observations. So why do we want to do this as a solid rocket boosters falling off? And I think the nose cone will fall off in a second. And I'll skip forward to my next slide. So there we go. So there's Herschel sitting on top of the rocket. Well, why do we want to look at the sky in these infrared wavelengths? I said we're looking at gas and dust between the stars. Well, here's a picture. It never comes out right on these screens because that's the sky at visible wavelengths. And the sky is mainly black with little spots of light over it. It doesn't come out particularly on projector screens. You can see a band across the middle, that's our galaxy, and a dark lanes across, which are lanes of dust in our galaxy. Top and bottom, there's not much there. That's looking out, up and down with respect to the disk of our galaxy. You can't see that many stars there. So that's the sky visible wavelength. If you look at a patch in the middle of the galaxy, and you say, well, it's very black there, that's because dust is obscuring my view, what can I say? I can say there's at least a certain amount of dust to be blocking all the light from the stars behind. So I'm essentially seeing the dust silhouetted. So I know there's at least a certain amount of dust. That's all I can say. If we look at the sky in these far infrared and submillimeter wavelengths, then we see an image that's very different. So that's an image from the Planck satellite. And the main galaxy, which is looking at similar wavelengths to Herschel, they overlap on this. And the main thing across the middle there is still our galaxy. Now the colour scheme is different. We're looking at non-visible wavelengths. You have to apply a colour to the different wavelengths anyways. False colour, if you like. But the galaxy now is by no means black. The galaxy is now very, very bright. And the blue wispy stuff you can see there is dust in that galaxy. That's light being emitted by dust and gas between the stars, primarily dust in the case of the blue stuff. And that's what Herschel is trying to study in our own galaxy, that dust and gas between the stars and how it's forming new stars. It can also look at other galaxies. So the first image that Herschel took was not this one. This is the galaxy M51, that many of you may well have seen. That's it in visible light. Herschel took this image a few months after it was launched in far infrared light, And you can see the similarity, there are spiral arms there. Now, Herschel sees the dust between the stars, so it actually sees those dark dust lanes. So these bits of M51 where there's nice dark regions are now glowing very brightly in Herschel's view. And the other thing about the Herschel images, I should say, is that the blue bits that you can see are emitting primarily at shorter wavelengths. That actually means they're emitted by warmer material. That light is emitted by warm material. So in the Herschel images, typically, blue stuff is warmer and the red stuff is colder. And the orangey, greeny, yellowy, murky stuff is somewhere in between. And to give you a sense of temperature scale, the blue stuff is typically going to be 100 or so degrees above absolute zero, so that puts it at minus 170 C or thereabouts. And the red stuff is going to be, say, 10 or 20 degrees above absolute zero, somewhere like that. So that puts it at minus 260 degrees C, minus 250, 260, that kind of range. So that's the image of M51, that's Herschel's first image. This is Spire's first image on the right, compared with the same image from NASA's Spitzer satellite, which looks at similar wavelengths. NASA's the Spitzer satellite has a much smaller mirror, so it doesn't have the same resolution. It also has much less sensitive detectors, and therefore doesn't see quite as much detail. So we compare the Spitzer image on the left with Herschel on the right. With Herschel on the right, you can start to see the spiral arms in this galaxy, which is Messier 74. You can also see some spots in the background. So if I go to the next slide, which is, that's the three colours, three wavelengths seen by the Spire instrument of this same galaxy. And you can see the galaxy in the centre, and you can see what looks like a speckle behind. It looks like static. It looks like you've got an old TV, and you get the snow on it when you're not tuned in. Not the blue no signal screen, the white and black snow you get. That's what it looks like. You could think it's static on the detectors, but then you look at those three images, they're from different detectors, so the static should be all very different. And you say, well, okay, ignoring the galaxy, there's a sequence of blobs down here in this image, but they're also there in this image and this image. And then equally there's a blob there, which is also there, and also there, and so on. And most of those blobs are in fact, pretty much all of them, are real. They're real objects. But what are they? I mean, that galaxy is, I forget, it was 30 million or 60 million million light years away, long way away. The other objects it's seeing there are primarily distant galaxies, rather than being millions of light years away, typically billions of light years away, all seen in the same image. So every dot in the background is a distant galaxy. So the power of Herschel is you can see these very, very faint objects at the same time as seeing the much brighter ones. Looking closer on to our galaxy, so here's a region in the sky in Taurus. This is the Taurus molecular cloud, it's in invisible light. You might be seeing the background stars, but then this dark wispy stuff. Herschel doesn't see the stars, he's going to see the dust. And this is typically what the dust is. It's tiny grains of silicate or carbon-like material. So a bit like grains of sand on the beach. Not actually grains of sand on the beach, but that kind of thing. Typically tens or hundreds of microns, so a hundredth or a tenth of a millimetre in size, so very, very small grains. So that's the Taurus, and that's what that dust looks like when it's shining with its own, glowing with its own light. That's Herschel's image of that same region. And we can show them both together. The dark regions invisible line up with the bright regions in far infrared. So let's run through a few other things that Herschel's seen. So this is a star-forming region in Aquila. So again, a region of the sky you may well have looked at. It's probably never looked quite like that before. The blue stuff, as I said, is warmer. The red stuff is cooler. Now, what's causing the blue and what's causing the red? The blue stuff is being heated, the blue dust there, the blue regions, being heated by the light of stars that have already formed, from stars that are currently forming. So there's a cluster of stars on the left, there's a smaller one over on the right that are heating the dust around them. The red stuff is much cooler. We call it galactic cirrus. It's just this wispy dust between the stars. And that is distributed in these, you can see filaments and tendrils and so on. You can also see some little red clumps. Now those are the first stages of star formation currently taking place. So that's the first stages of dust collapsing under gravity, slowly getting denser, but at the same time staying very, very cold. And eventually, in a few million, tens of millions of years, that will be dense enough that it will, stars will form in their centre. So those little red blobs, you can see it well, the orange blobs up at the top left, there's a couple down the bottom left, and so on. If you look carefully at that image and do the full analysis on it, there's something like 700 stars being formed in little clumps, just in that one image alone. There's also things like the Cocoon Nebula, which again you may have looked at with this. The Cocoon Nebula is over on the left, a very bright cluster of stars, which Herschel doesn't see, heating up the dust on the left, but then the much colder dust around it, and then these filaments of dust stretching away over to the right. And then you've probably all seen this image before. So that's something called the Pillars of Creation. That's an image from the Hubble Space Telescope from the 1990s. That's 3 pillars of gas and dust between the stars. It was like one of the most iconic images in astronomy. It's actually part of a bigger nebula. So it's bigger, it's the part of a nebula called the Eagle Nebula, M16, and that's where it is in reality. So there's a massive, this is visible light, there's a massive cluster of stars in the middle, blowing this cavity into space as the radiation from the stars pushes the gas and dust away, it blows this cavity into space. And the pillars are essentially what's left after most of that stuff has been eroded away. And there's more examples than just those 3 down the bottom left of it. There's pillars coming in from the top and from the left and from the right. But most of that dust at the top is black, you can't see it. So again, all you can say is there's at least enough there to block out the light from behind. You can't say much more about the dust until you look at it with Herschel. And then you can say, well, that's the same image to the same scale. The colour of the dust tells you the temperature. So this stuff is warm, it's being heated by these stars in the centre. And this stuff out here is cold. The stuff out there around the edges is much colder. And the brightness of the image tells you how much dust there is. So you can look at the density of the dust. And that really lets us say, well, this stuff here really is very dense. And there really are going to be stars forming there. And again, there are stars forming at the top, or about to form at the top in those little clumps. So we can tell an awful lot about stars forming in some of these iconic regions in our own galaxy, and also throughout the less iconic regions throughout. Herschel's doing massive surveys of our galaxy to try and find star formation as far and wide as it possibly can. The Cygnus region is another one it's looked at, and this is one of my favourite Herschel images today. This is a region called Cygnus X. It's that really dark black bit in the Cygnus rift in the middle of just to the left of Cygnus. I guess if we looked at Cygnus in the sky, I know it's bad form to say to the left. So this is a region of the sky in Cygnus. In visible light, this region is completely opaque, completely black. Far infrared light, we're seeing that dust which is blocking out the light, making it black to our eyes. We're seeing that dust glowing. You can see all sorts of structure. You can see more of these bubbles being blown by stars that are forming. And you can see some red clumps which are where stars are currently forming. I mean, these are all given names in catalogues, and they all have DR22 and DR21, all these sort of names. You can zoom in on one of them, and you can see, well, now in immense detail, you can see this massive filament with also little filaments coming off it. And the nature results indicate that this material seems to be being channeled along these filaments into that massive filament at the top, forming new stars as we speak. So again, this is going to form some of the most massive stars in our galaxy. It's one of the most active star-forming regions around. But it's not just 3 pictures that Herschel takes. It also has on board things called spectrometers. So this takes the range of colours and splits it into its individual wavelengths. And so that can look at something called the Orion Nebula, which you've probably heard of. So the Orion Nebula is an image of the space telescope in the background, but what's in the foreground is this spectrum from Herschel. So the spectrum says every spike you see is a specific wavelength that's emitted by a specific type of molecule. And so you can compare that with lab experiments and say what molecules are there. So you probably can't read the text, so I can read out a few of the molecules that they found. So we've got hydrogen sulfide, we've got methanol, a formal cation, some sulfur dioxide, dimethyl ether, formaldehyde, yummy, deuterium cyanide, delicious, some water, some sulfur dioxide, acrylonitrile, methanol, and more water. Now those are all organic chemicals. They contain, or most of those organic chemicals, they contain carbon, hydrogen, and oxygen. Now, organic chemicals just means that. It doesn't mean there's anything to do with life there. So, whatever you do, don't take away from this that I'm saying is life with the Orion Nebula, because I get shocked by the bosses. But there are these organic chemicals, and they're lying between the stars. And there's a big question in astrochemistry of how these kind of molecules and those that are more complex form. We know they can form in space because we've seen amino acids in meteorites, not with Herschel, but with other experiments. So we know very complex chemicals can form in space, but what environment should they form in, and how do they form? And how quickly do they form? Are they destroyed at all? And so on and so forth. So Herschel would try to understand that by looking at some of these molecules. It can look at other galaxies. I showed M51 earlier. You've probably seen the Andromeda Galaxy or pictures of it before. You may even seen it with your own eyes or through a telescope. So that's invisible light. In infrared light with Herschel, that orange stuff is showing those dark dust lanes are again glowing with Herschel's infrared light. And that's just taking away the visible light. Just leaves us with Herschel's view of it. And you can see there's this big ring, that dominates this big ring of orange dust most of the way out. So that's a massive ring. It's about 90,000 light years across. We don't know for sure how it got there, but it's possibly the Andromeda Galaxy's last meal, as it swallowed up a bigger galaxy, or as another smaller galaxy passed through the centre and essentially sent out ripples like a shockwave, like ripples on a pond. And that's as far as that ripple has got, 90,000 light years across, in however many billions of years ago the interaction was. But then, to come to another iconic image that you've probably seen before, this is the Hubble Deep Field. I showed it one of his sister images, if you like, right at the start. So this is an image taken, it's a patch of sky about the size of the head of a pin held at arm's length. Tiny, tiny patch of sky, stared at by the Hubble Space Telescope. And every spot in there is a galaxy. Well, Herschel does the same. He stares at a patch of sky. Actually stares at a bigger patch of sky. So if you take this image and shrink that down, that's an image of sky. It's about the same size as the full moon. So that's the end of your little finger held at arm's length. And every dot in that image is a galaxy, billions of light years away. So I've heard this described as an advert for carpet writing before. The colour of the galaxy tells you either the galaxy is made of very cold stuff, very cold dust, or it's very far, it's much further away. It's actually hard to tell the difference with Herschel at this level. So every dot there is a galaxy. Now, why are we seeing so many there? Well, these galaxies, we're seeing them as they were between, say, 3 and 10 billion years ago. And that period of the universe was the most active phase of star formation in the universe's entire history. That's when most stars were being formed. It's when most of the stars we see around us were formed. Now, the fact that there were lots of stars being formed also means there was lots of dust. Now, we've seen what dust does to visible light. It blocks out visible light. That means you can't see these galaxies, or it's very, very hard to see these galaxies in visible light. You need to look at the dust itself. So if you look in visible light, all you see is black. Black against the blackness of space. It doesn't give you much. So you can see the dust glowing in its own right. And you can also look at more larger regions of space. So here's a slightly bigger region. It's about, I think it's about 8 times wider than that previous one was. And again, every single dot in that image is a distant galaxy, billions of light years away. We're seeing that they were billions of years ago, and that's allowing Herschel to take the stuff it's seen in our galaxy, how stars form, and what environments they form in, and then say, well, how they behave in the distant galaxies in the early universe, and try and piece these together and see how galaxies are forming throughout the history of the universe, and how they're forming today, and try and build this bigger picture. And so we hope this bigger picture is getting more complete, and we're starting to understand more about how our universe has behaved over billions of years. And I'll leave it there.